Welcome to an exploration of how scientific methods can save your life in the most extreme situations on Earth. From freezing mountains to scorching deserts, science provides the tools and knowledge to survive when nature becomes hostile. Let's start with one of the deadliest environments: extreme cold. How does science help us survive freezing temperatures? Your body loses heat according to Newton's law of cooling, which describes how temperature difference drives heat transfer. The rate of heat loss equals negative HA times the difference between body temperature and environment temperature, where H is the heat transfer coefficient and A is surface area. An average adult has about 1.7 square meters of surface area exposed to the environment. Normal body temperature is 37 degrees Celsius, while Arctic temperatures can drop to minus 40 degrees Celsius. Here's a critical question: how long do you have before hypothermia sets in? Survival time equals body heat capacity times mass, divided by heat transfer coefficient times area times temperature difference. This diagram shows heat radiating from the human body into cold air. Without insulation, you lose heat rapidly through radiation, conduction, and convection. Numerically, if you're naked in minus 20 degrees Celsius, severe hypothermia occurs in approximately 30 minutes. The solution is to reduce the heat transfer coefficient by adding insulation layers that trap air. Proper clothing can reduce the heat transfer coefficient by a factor of 5, multiplying your survival time by 5. Now let's examine the opposite extreme: surviving in scorching deserts where water is scarce. The human body is approximately 60% water by mass, and maintaining this balance is critical for survival. For a 70-kilogram person, that's about 42 kilograms of water that must be maintained. You lose water through 4 main pathways: sweat, respiration, urine production, and skin evaporation. Here are the 4 pathways of water loss from the body. In extreme heat, sweating becomes the dominant pathway. Let's calculate the critical water loss rate in desert conditions. Water loss rate equals heat that must be dissipated divided by the latent heat of vaporization. The latent heat of vaporization for water is 2,260 kilojoules per kilogram. In a 45 degrees Celsius desert while walking, your body generates approximately 400 watts of heat. This gives a water loss rate of 400 watts divided by 2,260 kilojoules per kilogram, which equals approximately 0.64 kilograms per hour. Here's the crucial question: how long can you survive without water in these conditions? Losing 10% of body water is critical. That's 4.2 kilograms divided by 0.64 kilograms per hour, giving approximately 6.5 hours. The key survival strategy is to dramatically reduce activity and find shade, cutting heat generation to perhaps 100 watts. By resting in shade, survival time extends to approximately 26 hours without water. Moving to vertical extremes, let's explore the physics of surviving at high altitude where oxygen becomes scarce. Atmospheric pressure decreases exponentially as you climb higher, following a precise mathematical relationship. Pressure at height h equals sea level pressure times E to the negative h over h, where h is the scale height. The scale height h equals RT over mg, which is approximately 8,500 meters for Earth's atmosphere. This exponential curve shows how pressure drops with altitude. At 5,500 meters, pressure is only 50% of sea level. What matters for breathing is oxygen partial pressure, which is 21% of total atmospheric pressure. Oxygen partial pressure equals 0.21 times the total pressure at height h. At the summit of Mount Everest, 8,849 meters high, let's calculate oxygen availability. Pressure at Everest summit is 101.3 kilopascals times e to the negative 8,849 over 8,500, approximately 35 kilopascals. Oxygen partial pressure is then 0.21 times 35, which equals 7.4 kilopascals. Compare this to sea level, where oxygen partial pressure is 21 kilopascals. The question is, why does this reduced oxygen cause altitude sickness? Oxygen delivery to tissues equals hemoglobin concentration times oxygen saturation times cardiac output. At low oxygen partial pressure, hemoglobin saturation drops dramatically, following a sigmoid dissociation curve. This sigmoid curve shows hemoglobin saturation versus oxygen pressure. The red dot shows Everest conditions, green shows sea level. The body's survival adaptation is acclimatization, which increases red blood cell production over days to weeks. After acclimatization, hemoglobin concentration can increase to 1.5 times normal levels, compensating for lower saturation. In survival situations, food often becomes scarce. Let's examine the mathematics of human energy needs. Your basal metabolic rate is the energy required just to keep your body functioning at rest. For men, BMR in kilojoules per day equals 88.36 plus 13.4 times mass in kilograms plus 4.8 times height in centimeters minus 5.7 times age in years. For an average adult male of 70 kilograms, 175 centimeters tall and 30 years old, let's calculate. BMR equals 88.36 plus 938 plus 840 minus 171, approximately 1,695 kilojoules per day. With light activity like walking and basic survival tasks, multiply by 1.5 for total daily energy expenditure. Total daily energy expenditure is 1.5 times 1695, approximately 2,540 kilojoules per day, or 607 kilocalories. The critical question: how long can a human survive without any food? Your body stores energy primarily as fat, with some protein that can be metabolized in extreme starvation. Energy from fat equals fat mass times 37 kilojoules per gram. With 15% body fat, that's 0.15 times 70 kilograms, equaling 10.5 kilograms of fat. Total energy stored is 10.5 kilograms times 37,000 kilojoules per kilogram, equaling 388,500 kilojoules. Dividing by daily expenditure of 2,540 kilojoules, survival time is approximately 153 days. However, death typically occurs much sooner, around 60 days, due to organ failure and protein depletion before fat stores are exhausted. These bars show depletion of fat energy reserves and critical protein over time. Protein loss causes organ failure before fat is exhausted. Fire is perhaps the most critical survival tool. Let's examine the physics and mathematics of fire creation and maintenance. Fire requires three elements simultaneously: heat energy to reach ignition temperature, fuel to burn, and oxygen to sustain combustion. The fire triangle shows these three essential elements. Remove any one element and combustion cannot occur. Wood typically ignites at approximately 300 degrees Celsius, though this varies with wood type and moisture content. To reach ignition, heat energy Q equals mass times specific heat capacity times temperature change. Consider 10 grams of dry wood tinder starting at 20 degrees Celsius room temperature. The specific heat capacity of wood is approximately 1.7 kilojoules per kilogram Kelvin. Required heat is 0.01 kilograms times 1,700 joules per kilogram Kelvin times 280 Kelvin temperature rise, equaling 4,760 joules. The bow drill friction method converts mechanical work into heat through friction between wood surfaces. Friction power equals friction coefficient mu times normal force F times velocity versus. With vigorous bowing motion, you can achieve 50 newtons of force and 2 meters per second velocity. For wood-on-wood friction coefficient of 0.5, power is 0.5 times 50 times 2, equaling 50 watts. With 10% efficiency, time equals 4,760 joules, divided by 50 watts times 0.1, approximately 950 seconds, or 16 minutes of continuous effort. Once started, maintaining fire requires careful oxygen flow rate management for optimal combustion. Wood combustion follows this general equation where hydrocarbons react with oxygen to produce carbon dioxide, water, and heat energy. Clean water is essential for survival. Let's examine the physics of pathogen elimination through boiling. Waterborne pathogens include bacteria, viruses, and parasites that cause diseases like cholera, dysentery, and giardiasis. The question is, what is the physical mechanism by which boiling water kills these microorganisms? High temperatures cause protein denaturation, where proteins unfold and lose their biological function, killing the organism. The rate of denaturation follows Arrhenius equation, K equals A times E to the negative activation energy over RT. At 100 degrees Celsius boiling temperature, most pathogens are killed within 1 minute of exposure. Critically, altitude affects water boiling point due to reduced atmospheric pressure at elevation. Boiling temperature in Celsius approximately equals 100 minus 0.003, 4 times height in meters. At 3,000 meters elevation, water boils at approximately 90 degrees Celsius instead of 100. This linear relationship shows how boiling temperature decreases with altitude, requiring longer boiling times for safe water purification. Boiling time at altitude equals sea level time times 2 to the power of 100 minus boiling temperature divided by 10. Therefore, at 3,000 meters elevation, where water boils at 90 degrees, you should boil for 3 minutes instead of just 1 minute for safety. When lost without technology, celestial navigation uses mathematics and astronomy to find direction and position. The sun's position in the sky varies systematically with both time of day and your latitude on Earth. Solar altitude angle alpha follows this equation involving latitude phi, declination delta, and hour angle h. At solar noon, when the sun reaches its highest point, it is positioned due south if you're in the northern hemisphere. This diagram shows the sun's arc across the sky. The lowest point of the arc indicates south direction in the northern hemisphere. The shadow stick method uses the sun's shadow to determine cardinal directions with surprising accuracy. Place a vertical stick and mark its shadow tip at 2 different times, separated by at least 15 minutes. A line connecting these 2 marks runs approximately east to west due to the sun's apparent motion. Here's the shadow stick setup. 2 shadow tips are marked in red, and the green line connecting them indicates the east-west direction. At night, Polaris, the North Star, provides accurate north direction in the northern hemisphere because it sits nearly above Earth's rotational axis. Your latitude approximately equals the altitude angle of Polaris above the horizon, a remarkable navigational fact. Proper shelter design uses thermodynamics to maintain survivable temperatures inside despite extreme conditions outside. Heat transfer through shelter walls is governed by Fourier's law of thermal conduction. Heat flow rate equals negative thermal conductivity K times area A times temperature gradient. In steady state with wall thickness L between inside temperature T1 and outside temperature T2, we can simplify. Heat flow rate equals Ka times T1 minus T2 divided by wall thickness L. Practical question. How thick should the walls of a snow shelter be for survival in extreme cold? Thermal conductivity of packed snow is approximately 0.25 watts per meter Kelvin. Consider a scenario where inside temperature is 0 degrees Celsius and outside is minus 30 degrees Celsius. Target heat loss should be less than 300 watts total for a small 2 square meter shelter to be maintained by body heat. Setting up the equation, 300 watts equals 0.25 times 2 times 30 divided by L. Solving for L gives 15 divided by 300, equaling 0.05 meters or 5 centimeters minimum wall thickness. This diagram shows the snow shelter with 5 centimeters thick walls. The red arrows indicate heat loss, which must be minimized for survival.